I recently traveled to Ames, Iowa to visit PowerFilm Solar. Those of us in the ham radio universe might recognize something like this. This is their 120 watt foldable amorphous silicon panel, and I love it. I've been using PowerFilm panels for the better part of this year, and they're just absolutely phenomenal, and I'm humbled to have been invited up to visit their factory floor. In this video, we're going to get a tour from the president, Dan Steeler, and he's going to show us all about the manufacturing process of these amazing solar panels. I can tell you that I was in full nerd mode this entire time out there. Thank you very much to everyone at PowerFilm Solar for having me out there. If you're anything like a solar and battery nerd like me, this video should be fascinating. Electrical engineers, you should be drooling over the coolness of this as well. Or if you're just into seeing how cool stuff is built, this video is right up your alley. It's a bit of a long one, so grab some popcorn. Let's dive in.
All right, so welcome to PowerFilm. As many of you know, we make solar panels that are for basically applications that amount to helping with lives or livelihoods, remote, portable, expeditionary type solar panels. And so today we're going to get a little tour of the factory and see how the different product lines we make come to be. So first of all, we have about an 80,000 square foot facility here in Ames, Iowa in the US. We do all our manufacturing, design, manufacturing, assembly, engineering. Every part of the process is done here in Ames, Iowa. And so as we come into the factory here, you'll see we've got basically a large pole building type structure. As you look across the facility, you'll see a kind of a white wall in the background there. That's basically half of our facility. This half of the facility on this side is what I would call the back-end processing, or where we actually make stuff into a product. The other half is the semiconductor fab part, where we make the roll-to-roll amorphous silicon. And so we'll take a look at both halves today. But we'll start on this side and kind of work our way from one end to another. First, we're going to walk down there because the plant flows from the south end of the plant to the north end out the shipping dock. And as you know, we've got two different lines of products. Two main lines of products. The first one being the amorphous silicon, the second one being a crystalline silicon line of products. And they both run kind of in tandem down through the factory. And so if we look off to the left-hand side, what you see right now, this is our crystalline silicon initial assembly area. And so in the crystalline silicon area, we use some robots to do the initial panel assembly, which you can see one robot there that's operating right now. The robots will do cell placement, they'll do soldering, they'll do bus placement. They do all the initial tasks that are required in the process of making the panel. And so that's where the crystalline silicon panels will start. After they get done with the cobot, we've got some stations here that are actually optimized for ergonomics for the operators. And it's probably worth taking a look because they're kind of neat. When we first started doing crystalline silicon stuff, we actually did all hand assembly until we knew what kind of our demand was going to be and had enough demand to move to the robotics. So we started out with these types of stations. And the stations are set up so that you can have your panel out in the middle. You can do your cell placement. You can work on the panels, do soldering and stuff. Keep the rest of the thing clean, have a spot to lean on and work from when you're doing whatever operation it is, whether it be putting down flux, doing the soldering process, using the bus bar. One thing is that this is the kind of bus bars that we use. They're different than a lot of different technologies because the cell technology we use is a Maxion solar cell. The Maxion cells are really cool because they have basically positive and negative electrodes intertwined all the way across. So they're called an interdigited back contact cell because the positive and negative electrodes are interdigited like fingers going together on the back side. And so with these cells, you've got this one little piece of bus bar that goes on the edge and connects adjacent cells. And that gives them a lot of flexibility and a lot of durability. I mean, the whole back of the cell is a copper plated layer that's very thick. Only having the bus on the edge means that you don't have any metal to cause stress on the cells when they get bent or flexed. and leads to a really durable product from a crystalline silicon perspective. Now, the durability is not the same or not as good as what you'd see from amorphous silicon, but from a crystalline silicon perspective, it's probably we feel the best technology out there from a durability perspective. They're also some of the highest efficiency cells you can buy. The stuff that we get right now is about 23.5% to 24% efficient, which in solar, as I'm sure you know, is really related to the amount of power output per unit area. And so you can have a smaller package with a higher power output. And that's really beneficial in some cases for some of our customers, especially in applications like transportation, where if you're putting them on a truck fairing and trying to run your electric auxiliary power unit to do TVs, microwaves, whatever comfort systems you might have, air conditioning, you've only got a limited amount of space on the fairing of the tractor. And so every bit of efficiency you can get, the more power you can get in, is a major benefit in those cases. Let's take a little time and talk about amorphous silicon. So many are familiar with the amorphous silicon foldables that we make. We'll look at the fab in a little bit, but once a roll comes out of the fab, the first thing that happens is it goes through a process of being qualified for production. And what that consists of is first coming over to this machine. Now, this machine is a auto testing machine. And so we take a roll of foldable material. Our rolls are about 1/3 of a kilometer long, and we'll load it on this guy. And this is a light box. It's got a proprietary LED simulator or LED light source that we made here, designed and made at PowerFilm. And the light source itself matches the solar spectrum outdoors in the area that the amorphous silicon actually absorbs. So it's an outdoor match indoors. So we test everything at full power, quarter sun power, basically. The full power tells us, is it passing spec? The quarter sun tells us, are there any issues on the lower light level that customers would run into? Is there something that's causing a shunt or going to limit the low light intensity performance? Because for us, we know very few times is a panel in an ideal situation where you're getting full sun on it, right? It's laying out flat on the ground, might have partial shade, it could be a cloudy day. And so we test both 100% and quarter sun and have a specific guaranteed limit on quarter sun performance for that reason, because it's important that the panel works at the lower light levels when, a lot of the time that's how they're actually used. So each panel passes through the light box, it gets tested, and as it comes across the machine, it actually goes through this station here, which is a printer. And so the printer actually prints a little UV code on each of the panels that says what the grade is, what the run number is, the frame number, all that kind of stuff. So that gets printed on the panel in UV, and then it basically winds back up. And so in the end, our QC technician will go to his computer and he'll pull it up and basically get a printout report that says all the frames, it might be 1,300 or 1,500 solar modules long on that roll. It says what each module's grade was, what it measured as, and so basically what your expected performance is. And so we've got a performance map of every single roll of material that we make. After this, the material goes to our laminators. And so let's just walk over there for the sake of following the process through the way it would follow. So after doing the roll mapping on this, and when you know what the performance is, then we have to make a choice as far as what product it's going to go into. Is it going to go into a foldable product, a rollable product, some sort of custom OEM product? Once we've made that choice, then we'll decide where it goes next. And so what we're going to do is we're going to follow the foldable process through the foldables through their whole process. So if it's a foldable, it comes back to this machine then, and we put down the bus tape that goes along the edges. And so you can see on the end here, there's the tape heads, and the roll of material will basically run through in a continuous process and put bus tape on the two edges. And the bus tape's needed to basically decrease the resistance of those edge bus bars so that you're able to get the most power out of the modules. If you don't put the bus tape down, you could make contact with the silver prints that are along the edges, but the resistivity of the silver is higher, and you're going to lose a lot just in the resistance of the panel itself. And so put the bus tape down. After the bus tape goes down, then we're going to go over to a lamination process. Now, the one thing to note that also happens at this machine at the same time the bus tape's going down is we actually have to put in an interleave layer of like polyester, because the bus tape has some thickness and we can't roll up the film itself without having some sort of interleave over there to take up the thickness in the middle when you've got all the extra bus thickness on the edges. And so what comes out of this machine is a roll of solder material with bus on it, and then with that polyester interleave already in, ready for lamination. All right, for the lamination process, we actually use a pretty standard laminator. This is just a 64-inch AGL laminator, which is the standard you would find for a lot of graphics lamination type stuff. Nothing really special or crazy there. The setup you see here, you would have your solar material on this take-up that came from over at the taper. This one, actually, this right here is the interleaf we were talking about before, and so this is the material that we put in between to take up that extra gap with the tape. It's really just a metallized polyester material. Nothing super special. And so what would happen here is we would feed in the solar material and put down the layers of ETFE, TPU, and the backside EVA polyester that's used as a stiffener, all at one shot going through the machine. And so that all goes through the laminator and gets taken up on the other side. And the output of this then is basically that roll of material. It's amorphous silicon with the front and back encapsulants on and the bus tape. And so from here, we're going to take the material and we're going to check out how we get it singulated off the roll into individual modules, which is on our auto die cutter. So we're in the auto die cutter room. And so right now, this comes after we go through and do the lamination process. So we've gone through and we've auto tested. We did the auto taping, put the bus bar on the edges, which you won't see actually on this web here. This one's just here for demonstration because we didn't have actual piece of material that was in the right process, but it gives you an idea how stuff flows through. So normally it would be auto taped. It would have the lamination on it, and so it would be already laminated. And then we'd come to this part of the process. And so this is our auto die cutting machine. Basically what happens is you start feeding in the roll here. You'll see inside here that there's a UV purpley light. Maybe it's a deep blue. That's used for our registration. So on the edge of the web, you can see that there are these diamonds. So there's squares with rectangles with diamonds in the middle. Those rectangles we use to register the die press to a specific location. And so it'll register on both sides, make sure that it's skewed correctly. And then it uses a steel rule die to basically come down and cut out each of the individual modules. And so when we cut the modules, we actually have a little piece of the die that does not cut through. And so they remain on the roll as it comes out the back of the die cutter here. They stay together until you get out to this point, and then you'll have somebody on this side that's actually freeing them from the web and loading them in boxes as the individual modules then that we saw that get fed into the pick and place machine. But this room has all kinds of static protection because at this point the static there tends to be a lot of static because you've got the laminates pulling off of each other and creating static electricity. And since we're at this point, we are exposing the metal on the edges of the modules, on this cut edge. That exposes or gives us the potential to create shunts and defects because of the static electricity. And so we keep this room very humid. We have other static mitigation techniques in place that basically protect the film during the die cutting process. By the time it gets out to the consumer, it's already protected because when we go through the other processes like the George Foreman especially, it reflows that adhesive and that coats over those edges where there was the exposure and the potential to have shorts created, and so it's no longer a problem. But at this point in the process, static is a major issue. Yep, so here's the raw film that we use for the foldables. This is what we would call a material that went through our down web process. meaning that all the laser processing and printing happens in the downweb direction in a continuous fashion. And so each one of these areas right here is one solar module that you would see on a foldable panel. And so this would be the state of the run when it went to that auto testing machine to be tested. Right now, it doesn't have any bus bars on the edges. It's just our silver printed edges. And so when it goes to the auto tester actually has a set of phosphor bronze type probes that come down on that silver print and do the testing. This would also then be the state that you would feed into the taper. And so it would go in like this, and it would come out with the tape on it. The tape is like, let me see if I can find a piece. The tape that we use is kind of special. It's a 3M product. It's got this, it's basically a tin-coated copper foil, but it has this special checker pattern. And on the back side of the tape, you're not going to be able to see it, but on the back side of the tape, the adhesive is not covering the full back of it. The checkered pattern works to basically hold some bare metal parts of the tape in contact with the silver bus that you want. And so you've got the waffles that are sticking up on the top actually have adhesive down in the valleys of them, and the parts that are pushed down are bare copper or bare metal. And so when you stick it down on there, the adhesive holds the bare metal tight to the silver print, which gives you your electrical connection to the module. And once you get the encapsulation on that, you know it's all stuck together with glue. It's incredibly durable. I mean, we run these things to a couple thousand roll cycles, 2,000 to 3,000 when we test. And what that means is it goes over a 3-inch roller and a 6-inch roller 2,000 to 3,000 times. And you know, stick them back out, take them outside, test them. There's no degradation. You know, it doesn't peel away. It's really held in place. And so it's some really cool tape. A lot of the stuff that you see on the foldables is actually this, which is this same tape, but it's got like a polyester cosmetic black liner on top just to give it a little cleaner look. But the actual tape underneath is the same form fit function. Yeah, and so then this tape actually gets applied by the taper just like that on the edges. And so the output of that taper ends up being a module like this with the cosmetic black tape on the edge ready for lamination.
And that's what it looks like after...
Yeah, so after die cutting, you know, we've been through the process, we've tested it. We've got the bus tape on the edges, which you can see the black cosmetic bus tape that we talked about. It's laminated now. We've got ETFE on the front. We've got a polyester with the EVA on the back as an adhesive. And so now it's ready for the next step. And so after being die cut out of the roll, what we do next is we actually take and load these panels into this robot. And so each of these bins get loaded up with panels like this. Either, if it's a 60 watt, we only use a small panel. If it's a 120 watt, you'd see like a double wide panel. And this yellow robot, the welding robot, will actually pick up the panels. Since it's not running, what you'll see is the robot would come over here, would pick up a panel. It'll bring it over here and set it down and do a visual inspection on it. When it does the visual inspection, it's looking to make sure that there's no defects that it sees visually at the panel, and then also that the orientation of the fingers, positive to negative, are correct. If that's all looks good, it'll set it up here and transfer it to this other robot. The other robot then will come over, he'll pick it up and place it wherever it's supposed to be placed on the fabric to put the whole module together. Once it's placed on the fabric, this guy actually has a set of heaters that come down on the two sides and tack it, and the thermal adhesives in place, so it's tacked in place where it's supposed to be. Once everything's all done and put together, the robot then also has a laser on it, a CO2 laser that takes and cuts the fabric and pulls it forward off of the robot system to go into the wiring cell. This is what the output from the pick and place machine would look like. The robot went through, it put all the different individual modules in the spots they were supposed to be, tacked them down with heat, and now the solar panel comes here to be wired. And so during the wiring process, what we do, this is a manual process here. We've got some people who are very skilled with soldering that do this. They will take this wire, which is a really special wire. It's called Litz wire. And basically, it's a multi-strand wire that every individual strand is enamel coated. And so it makes it very flexible so that they're small strands, they're woven, enamel coated. The enamel allows the strands actually to rub against each other and slide easily. And so it gives us incredible durability. And so we'll come through with the soldering iron. Somebody would take and go through the encapsulant, solder the wire down like this across the cells. At each of the joints here, make a loop for some strain relief in the wire. And you continue down the line and do soldering and loops until you get everything connected.
Does it go through the center or just around the edges?
It'll go through the center as well, yeah. So if you look at this one's actually set up to be a 21 volt type module. And so it's got positive is at where the fingers are pointing from, and negative is where the fingers point to. So you can see they're pointing this direction, so positive to negative. This one's positive to negative, positive to negative. So the way this module will get wired is you'd have a piece of Litz wire going down each of these tracks, and then they would actually get wired together at the top and at the bottom. So you got some like a double redundancy of connections between individual things. And so these are actually all end up in series in the end. On the standard 120 and 60 watt panels, the interesting thing is that particular single module, which one of these would be a module, solar module, that single module actually puts out the full 15 volt voltage that you would want. And so every single piece is connected in parallel on a standard 60 or 120, and every single piece is able to produce the required voltage. So, if you shade this one, all you lose is whatever would be in the shade from that one. You don't lose any more because it's not series connected. The problem you have with a lot of crystalline panels is in order to get, since the crystalline cells are very large and not very customizable or not easily customizable without cutting them, you end up with one series string of cells through a panel. And then if you start shading parts of the panel, you lose a lot more than just the little individual shaded part. But since each of these are standing alone on a PowerFilm 120 or 60 or 120, you don't lose as much, and it performs better in shading and lower light type, non-ideal type atmospheres. It'll perform better if you're off angle. If you have a crystalline one that's off angle, if you're partially shaded or low light in one area versus the other areas, that'll limit some of your performance of the overall thing. And so that's one of the really cool things about amorphous silicon. Your power per area is going to be lower, right? And amorphous silicon is probably about 6% efficient, where the crystalline silicon, again, is in that 24% efficient range. But there's a lot of benefits in durability and shade tolerance in other areas.
Does each module represent a certain number of watts?
Yes, yeah.
So you put a certain number of modules in a 60 watt and then double that number for the 120
Correct.
watt?
Yeah, so if you look at the structure of the 60 and the 120s, the 60s are put together with like 24 of those small downweb modules that we showed earlier. The 120s are put together with 24 modules, but they're double the size.
Okay.
So they're a two-strip module rather than just a single strip module.
Okay.
Here to do the sewing process. And so we're gonna make Gerald really nervous right now. But yeah, so what Gerald's doing right now is he's making the flaps for the individual modules. So it's not necessarily sewing together the solar yet, but making the flap that goes around the outside that keeps it together. In these areas is where we do the larger panels. And so we do a lot of work in lean manufacturing, trying to optimize our process and make it so that it's the most efficient, so that it's easy for operators, so it's ergonomic, any of those sorts of things. And we've got these strange tables that actually came out of one of our lean events. It was an event, and I think it was one of the assemblers actually that said, it's so hard to push these things through the sewing machine. When you got that big 120 watt to push through the sewing machine, we need some way to make it so it doesn't bunch up. Why don't we just make an air hockey table? So the engineers said, well, yeah, we can do that. So we've got these big air hockey tables basically that help float the panels through the sewing machines during the process.
Oh, that is
so
cool.
Large things with a low resistance. it's always amazing the things that people come up with. You know, when you're having the discussions, you're like, how can we make this better? And it's like, well, I know, you never know who's going to have the idea, but there's always some cool things that come out of it. Once we get through the process and we'd have the stuff wired and sewn, the modules go into this guy, which is, we call him the George Foreman. He's our big heat press. Haven't been making hamburgers on him, but suppose you could. But they go in here, and what that does is it actually allows the laminate to reflow. So it gets, at the pick and place, we just tack the two edges of the solar modules down to the fabric. In here, it allows us to tack the whole back of the modules down so they have a good bond to the fabric. It also takes and reflows the material around each of the solder joints where we soldered the Litz wire on to get a better moisture seal, and pushes a little bit of the laminate outside to seal the edges of each of the solar modules as well. So this is our big heat press called George Foreman. His job is really kind of do the final tack and seal down of everything in the lamination stack on the foldables. When we looked at the ones there, the panels were, you could lift up the one side of them, they only tacked on one side. We're now, after coming through, it's tacked all the way across. You can't separate it from the fabric like you could do before. Once we've been through sewing and George Foreman, the panels come to here for the final finishing stuff. And so depending on what it is, it's going to get a grommet. So we've got different size grometers and different grommets for different applications. It's going to get a pigtail and a junction box put on. And so we've got our selection of different types of pigtails that we would use for different products up here, like a SAE in some cases. In some cases, it's a Delphi. Could be other types of connectors. So you'd pick out the connector you want, you'd put it down, add in a circuit board. So for the 60s and 120s, we've got this little diode board. It has a lot of different protection diodes on it. It has a bypass diode, a reverse protection diode. The bypass diode actually is in conjunction with this guy, which is a PTC. So if it gets hooked up backwards, it really acts as a reverse protection type thing. And the PTC, the diode will shunt the current through the PTC, and that will then blow, that'll blow or go open, high resistance, and take the solar module out of the circuit. So if it gets hooked up backwards, you're not putting a reverse voltage on the panel itself. It also has just a reverse blocking diode, or not a forward blocking diode, so that at night the panel doesn't consume any power from a battery or something that you have it hooked up to. Because at night when it's dark out, now the solar panel is going to look like a diode itself, and so it would be able to consume power just like that. So this would get put inside, soldered down to your panel. You'd add in your pigtail that you wanted, put your junction box over the top. We've got a little bit of adhesive in here, a silicone adhesive that goes in as well, or silicone caulk type thing that goes in as well to protect it. We use some Humaseal on the boards and the solder connections before they go in, which is like a urethane potent to protect as well. So you've got that. You've got the silicone as a secondary protection. And then the junction boxes with the PC boards in get riveted onto the panels themselves. Once we get through the finishing process and have our junction boxes on, the panels finished, it's ready to be boxed up. It goes here first for its final test. And so we 100% test every product that's going out the door. And again, this is a large area tester that is made with the same LEDs that we talked about at the auto test stage when we were doing the auto roll-to-roll testing. This guy gives us that same outdoor spectrum and allows us to test the panels at basically full sun power and make sure that everything's functioning properly. All the connections are good. There's no cold solder joints, high resistance joints or anything in the thing, and that it's ready to go. And so every panel gets tested on here. We log the test data and correlated with the serial number from the panel, so that if there are issues, we can come back and we can see, what did it test like when it left the factory. To do the test, we actually use an electronic load. The loads that we use are BK 8500s. They do a pretty good job. They're not necessarily the most high precision instrument, but they're a good workhorse electronic load. and they've served us pretty well day in and day out doing our final test stuff. After final test, everything gets boxed then and then heads out the shipping dock or heads into our inventory cage. Crystalline products or our rollable products, we use a different process. So you saw earlier how the crystalline panels were initially assembled. Once you get through the cell placement and putting the bus bars down, soldering, you get through all those checks, the panels actually have fiberglass laid on the backside and a layer of EVA underneath the fiberglass between the cells and the fiberglass that acts as an adhesive. From that stage, they'll come and be loaded into these large vacuum laminators. Now, the process is basically the same for a rollable. You'll go through and you'll have the material taped. You'll get whatever types of junction boxes or anything that you might need on it, or not junction boxes, but printed circuit boards or whatever you need for interconnecting everything. And then they'll get loaded into a vacuum laminator with the full stack. Now, we use the vacuum laminator basically for products that need to have an edge seal that you want to get like a permanent outdoor, 10 to 20 year lifetime product out. So if you're going to take something and you're going to put it outdoors for 10 years or 20 years, what you want something like a rollable configuration. The vacuum lamination is much slower than the roll lamination that we have for the foldables, but it provides a 1/4 inch to a 1/2 inch seal around the whole product, which basically encases it so that no matter what you can do, you're not going to get moisture in there. We've got panels that actually get run underwater. And so the panels that are used underwater use this type of thing, and there's no issues with running them in salt water or anything long term. They are indeed sealed. And so the vacuum lamination process basically just sucks all the air out of the product and then heats up and allows the thermal adhesives, which are thermal polyurethanes or EVAs or polyolefin elastomers. It allows them to melt and flow around the whole product and basically seal everything in. We use both adhesives that are cross-linking and non-cross-linking depending on the application. The cross-linking adhesives, you have to be a little bit careful in the vacuum lamination processing that you get fully cross-linked so that they do have that long-term performance. The non-cross-linking ones, it doesn't matter. You just have to make sure they flow and do what you look the way you want them to look in the end. You don't want a lot of bubbles or anything like that. Small bubbles inside towards the center of the panels are not a problem. Bubbles that would extend to the outside would be a problem. But yeah, so this is the process that you would use for the lamination on the rollables or the crystalline type products. From here, you would go to a finishing cell, much like the foldable finishing cell, and you do your junction box additions, riveting, you'd add your diodes, any of those back-end processes. All right, so we're actually going to talk about this guy. This guy is our large laser table, and we use him for a lot of different things, but the most common thing is doing the final trim on the encapsulation to get a good edge. So when we go through a vacuum lamination process with a lot of products, the products come out just like these guys over here. And so they've got this large border of encapsulant that's around the outside. And so what the laser does is we have the laser come in and we have it trained for each of the different products. And so on each product we know there's a specific feature that it's going to look for. And so it's got a vision system and it's going to look for, say, this one dog bone in the corner on this side and then the dog bone in the corner on the other side to get its alignment correct. Once it knows what its alignment is, it knows what its cut path is, and it'll take and cut around the panels to give you a nice edge. And so you go from having an edge like this with that extra material to having a really, really nice smooth edge and a consistent size in the product. And we also do stuff like cut out the holes on the laser if you have products with holes. And you can see, I don't know if you can see it, but if you can feel that it's a very smooth, nice, clean edge that you end up with the laser. Another part of PowerFilm's business since our business is really, making a good chunk of our business actually is making custom panels for our customers. And so those custom panels, many of them are going into things like the trucking industry. And so in our trucking panels, we make crystalline panels, but we also offer things like cable assemblies and charge controllers. And we win business by providing complete solutions, because a solar panel by itself doesn't do much. You need to know how you're going to get the solar panel, the power from it to your batteries, and be able to actually charge the batteries. And so what we do is we offer different types of cable assemblies, different charge controllers, and we'll do a lot of the custom cabling here. And so we've got machines like this guy, which are set up just to put abrasion tape on cable. So a lot of the automotive customers want an automotive abrasion tape added. So we'll add abrasion tape to the cables. We've got wire processors, and the wire processing machines themselves will take and cut to length. They'll strip. They'll do all those sorts of things, and so you can create whatever size pigtails that you might want with them. We've got overmolding, so we'll do overmolding of the cables and overmolding of the connectors. So if I look here, this would be an example of, this is actually a pigtail for one of our customers that wants a long pigtail. Don't want any connectors on the roof of the vehicle, and so we've got a long connection. You've got the little overmold section here, which goes in the junction box, and that's actually done here on our overmold machine. You can see that there's abrasion tape on the outside, and then a weather pack connector on the other end. So that's kind of what we do for custom cable assemblies. If you look over here, we actually put together our own charge controller electronics. We've designed the charge controller electronics here. We've got a partner in Iowa actually that does all the PCB population and stuff. So that's all done in the US and actually in Iowa to make the circuit boards. And then we do the final assembly on charge controllers here. And so right now you can see we're putting cables on these guys. We're getting the circuit board in here. Once they get all put together here, they'll actually go to our potting station to be fully potted in place so that they're weather sealed and they're very durable, ready to go out and be on the roof of a truck or whatever application you might have.
Are those sold individually, or do they come with like a paneling system?
So most of the charge controllers that we sell, any stuff that we sell with this type of charge controller that's PowerFilm branded or Soltronics branded. Soltronics is our crystalline brand. They actually come integrated into the panel. So you'd buy the panel with the charge controller and you'd be able to plug it straight into your battery.
Gotcha.
In this case, this is for one of our OEM customers, and so this charge controller is not going on the panel, it's going down below in a different position. So they're taking the lead from the panel down to the charge controller, and this charge controller will sit next to their battery.
Gotcha.
So PowerFilm actually does the semiconductor fabrication of the amorphous silicon products right at our site here in Iowa. And so it starts with a pre-bake process. So what we buy is a polyimide plastic, and the polyimide is a gold-colored, high-temperature plastic material. This guy would be an example. If you look here, when I peel it back, you can see that kind of the amber color. The polyimides that we use are anywhere from about 1 mil thick up to 2 mils thick, so 25 to 50 microns. When you get a plastics tend to absorb moisture over time. They're kind of like a sponge. You don't really think of them that way, but if you think about, if you put something in a plastic bag at your house, say you put your Cheerios in there, over time your Cheerios still get stale, and that's because there is moisture that passes through. And so what we need to do before we can do our semiconductor processing is we need to get rid of that moisture and bring it to a base state. And so we've got these two machines here, PB1 and PB2, and what they are is our pre-bake machines. And so in the pre-bake machines, basically all we do is we take and we run the plastic through a series of heaters, and we boil the moisture out of the material under vacuum. And so they're basically vacuum ovens, more or less. And so you'll load in a roll of material, you'll pass it through here, The material at this point, we start with rolls that are about 750 meters long. And so we'll run 750 meters through the baking process, get rid of all the moisture, and then we're ready to move on to the next step. And so when we move from this step to the next step, we're going to go into the metal machine, but we want to make sure that we do it quickly because we don't want to give the polyimide a chance to absorb moisture again. So things will move from here directly into the next set of machines down the line here. Now, these two machines are what we call our metal machines. And so the metal machines put down all the metal that we need for the back contact on the amorphous silicon or on for the solar cells. And they do that with a sputtering process. And so we use stainless steel as an adhesion layer to the plastic first. So first some stainless steel goes down. Then we use a stack of aluminum, and the aluminum is put down in such a way that it creates a texture. So it's not a smooth, we don't want a smooth mirror like aluminum, because a smooth mirror like aluminum makes it really difficult for the amorphous silicon to stick to it. We need a little bit of texture to help it stick. And so we put down a layer of stainless, which helps the aluminum adhere to the polyimide. Then we put down a layer of textured aluminum, which gives us the conductivity we need to get the power out of the device in the end. And it also gives us the texture we need to make sure that the amorphous silicon sticks when we put it in the process. Now, a sputtering process, if you're not familiar with it, is basically, I like to think of it as like you're watching somebody run down a beach. And as they're running down the beach, every time their foot falls in the sand gets kind of pushed up. You see some pick up and fly up in the air, and some of it sticks to the side of your leg. Well, that's basically what we're doing here. We've got a chunk, which is just a piece of aluminum bar or stainless steel bar. We've got argon gas in there, and the argon gas, we put in a large electric field. So it basically shaves off some of the electrons off the outer shell and ionizes it. And then the combination of an electric and a magnetic field pulls those heavy ions in towards the stainless or aluminum bar. When they hit that bar, they actually physically chip off little pieces of metal. And so we want to make sure that the geometry is such when our polyimide is moving through there that the first thing that metal hits is our polyimide, and it'll stick to it then. And so basically by chipping the material off of the metal bar and having the polyimide go by, we build up a layer of metal on the material.
This is vapor deposition?
It's a vapor deposition, yeah. It would be a physical vapor deposition process.
You want to show
Yep.
the target?
So this would be an example. This one is one of our stainless steel targets that's been used. And it started out as a flat bar, but because of the magnetic field that's in the cathode, in the sputtering machine, it actually pulls the ions into this particular pattern and creates a racetrack around it. And so you can see it's just basically chipped away a whole bunch of the bar to create this racetrack, and that's the material that goes out and gets deposited on the plastic. Okay, so from here then, we're gonna switch gears and we'll go over to these guys. These guys are our amorphous silicon machines. And so what you'll find in here, most of the modules we make, or most of the amorphous silicon we make, is a tandem amorphous silicon. The reason we use a tandem cell is because amorphous silicon suffers from an effect called Stabler-Wronski. And so Stabler-Wronski is basically a light-induced degradation. And you'll see it happen over the first 100 hours of panel use in light, and then it pretty much stabilizes. But the amount of degradation is really proportional to the thickness of your light-absorbing layers. And so if we do a tandem cell, we decrease the thickness of both the light-absorbing layers, which decreases the amount of degradation that you see in the overall panel itself. And so that's one reason that we do it. The second reason that we use a tandem cell is because the tandem cell gives us twice as much voltage, so that we use less real estate on areas where we interconnect cells together, and we're able to use more of it as active area for producing power. So what that means is a single junction cell would be an N layer or N-doped semiconductor layer, a intrinsic layer in the amorphous silicon, or we'd call it I, and then a P-doped layer. And so that would make up one semiconductor or one solar cell junction. In a tandem cell, we basically have two sets of those. So we have NIP, NIP. And so inside this vacuum system, we have basically 6 zones that are doing plasma-enhanced chemical vapor deposition. The vapor deposition takes place at 13.5 megahertz in all but one box. In one box, we actually use a 40 megahertz plasma. It's done by bringing in a series of different gases. So we use hydrogen and silane for making the amorphous silicon itself. The silane provides the silicon atoms. The hydrogen actually provides passivation that gives you a higher quality film or higher quality solar cell. In the N layers, we actually use a phosphine gas, which provides a extra electron, which gives you kind of a negative charge profile in the amorphous silicon. So phosphorus is what we want out of that. In the P layers, we use the diboron gas to get a boron atom, and that boron provides you with a more of a positive charged area. And that basically, the negative area and the positive area that's separated by that intrinsic layer allows you to have to produce the voltage and get the separation that you need to actually pull power out or pull your electrons out of the amorphous silicon when the sun's shining on it. And that gives you the power from the solar cell. The plasma-enhanced chemical vapor deposition process takes place at, between 300 and 700 torr, or millitorr, so it's fairly low pressure. So this is our laser scribing room. This is one of, well, I guess there's 3 different areas that have different environmental controls. There's the main factory, which we environmentally control humidity in, but we don't control it at a really high level. We try to keep it in the 20 to 40% range, so it's a pretty wide process window. In here, we try to keep the actual air coming in filtered and try to keep the debris down because we're running the lasers in this particular room. We also try to keep it a little bit cooler and more temperature stabilized for the laser processes. In the die cutting room that we've talked about earlier, you walk in there and it feels like a swamp. And so we try to keep the humidity really high in the die cutting room because the die cutting process with the plastics tends to create a lot of static electricity. And the static electricity, if it's discharged inappropriately, will damage the solar material. And so those are kind of our 3 environmental areas. In here, we do all our laser scribing. And so laser scribing is necessary for us because that's how we define what the cells are. That's how we basically stitch them together and make sure that they function as individual cells. And so, should have brought a piece of material in. We talked a little bit about cells earlier with fingers in the direction they're pointing. We'll see. We can get something in later and look at it again in more detail. But basically, after the amorphous silicon process, we go through a series of scribing and screen printing processes. And the first one in that series is what we call a through scribe. And so the through scribe, we have to decide what are we making. Basically that's what cell size is it, what module size is it, what does that need to be? So in the case of like the 60 or 120 watt foldables, we use basically 160 millimeter long cell, and we have the cells that are 2¼ centimeters wide. And so first we define, what is that? And so we use a 1040 nanometer laser. We scribe on, like in this case, this would be the scriber that you would use for the downweb process. And so it's a continuous scribe. You load your material here, and it actually runs on this drum. And you can see on the drum, there's lines where the laser actually etches the aluminum drum that it runs on itself. The trick really is that the polyimide plastic does not absorb that 1040 nanometer laser. And so it allows you to scribe the metals and the silicons without actually cutting the plastic, so that you end up with everything on one substrate and you end up with something that's really, really durable in that case. After you do your through scribe, then you go to the printing room. And so we'll go there and talk about that in a little bit. But I wanted to talk about one more thing while we're here. So we've got these scribers, which we call downweb scribers because the material runs past the lasers and it goes continuously. So it's a fast process. You could scribe something on here in a full roll of silicon in 40 minutes or so. Over here are our other scribers. And these guys, we would consider this a crossweb process because the material will advance. Of course, it advances in the direction of the rollers here. And then the scribing actually takes place in the transverse direction to the web, so across the web rather than the downweb direction. So it's a step and repeat process. So stuff that we do in high volumes, like the foldables, they all go towards the downweb process because it's faster and it's more efficient. But we do a lot of customization for OEM customers. And in that customization, many of the custom modules come through the crossweb process because it's really inexpensive and fast to change. And so we can prototype things on the crossweb process quickly that we couldn't do in like the downweb process. The downweb process, all the laser optics are really fixed. It's hard to change, but it gives you the efficiency. The downside to this process being easy to change and stuff is that the same run that took 45 minutes there, now over here is taking 4 hours. And so a trade-off between the different processing techniques. But again, a very important tool for us since we do a lot of customization. So after the first laser scribing step, once the cells are defined, then they come in here for 2 printing steps. And so we use screen printers. And the screen printers are really pretty similar. Actually, they are textile screen printers. There's nothing really fancy about that other than we've heavily modified them. We use regular textile screen printing things. We use the regular screens even. But we have one that does, again, the crossweb process and one that does the downweb process. And now, same issue as before with the lasers. The crossweb process uses flat screens. We can actually shoot the screens here ourselves. So if we have a new pattern or something, we'll order an emulsion from a company up in Minnesota. They'll send it down in a couple days. We can shoot the screen and develop it right here. And then we're up and running on the crossweb printer. But it's, again, step and repeat. It's slow. So it'll take 4 to 5 hours to do a roll of material on the crossweb printer. On the downweb printer, it actually uses a cylindrical screen that would fit in this area. And let me go grab a cylindrical screen quick. So instead of a flat screen, we use a cylindrical screen like this, which allows us to run continuously. So we can run very quickly. So a run on this guy could be as short as 15 minutes for the same run that would take 4 to 5 hours on the other one. So it's very fast, but it's not very flexible. And so these screens we can't make here. We have to order in. And a screen set for this guy is going to cost more like $2,000 to $3,000 versus about $100 on the other one. And so it's not as flexible, and it's more expensive, but it's much, much faster. So all our high volume stuff we push through this type of screen printer. Now, the inks that we use are kind of interesting because we use a polymer, 100% solids, polymer black ink for it, an insulator ink. And basically the insulator ink has to cover up all the places where we scribe lines before. So when we put the top conducting coating on it, we don't short down from where our initial through scribes. It's UV curable, so it runs through and gets cured on a UV lamp, and it works really well. But we put down 2 lines with the insulators. First we cover the one line, and then we put a second line on top of the silicon, which is going to act as a beam block in the end for us. After we get done with ITO, we go back and actually scribe that whole top metal coating so that it's divided, not shorted between cells on top. The silver print is a kind of a standard silver flake ink. It has about like a D90 of, I think, 15 microns for a flake size. The conductivity is somewhere around 10 milliohms per square. And it acts as the top grid then that's on the material. And so it's a thermal cure, not a UV cure. So we have IR ovens on the back of both of the systems, and the IR heaters will cure this over ink and get it in place. And so we do the 2 prints back to back. First we do the polymer black ink, and then we do the silver ink. And once we get done with the 2 prints, then the material goes back to the scribing room, which we were just in, and it goes through a laser welding process. And so we do basically a stitched laser weld down the lines to weld that silver to that bottom aluminum. Once we have that welded together, then it actually goes over here to the ITO machine. So let me put this back and we'll walk out there. So these 2 machines are very similar to the metal machines. Again, it's the same type of sputtering process, only this time we're putting down indium tin oxide. And so the indium tin oxide is a cool material. It's whether or not you're familiar with it, you certainly have it in your house. It's on your cell phones, it's on your LCD TVs. It's a clear material that actually conducts electricity, and so that's why we use it on top of the solar cells. But we put this down with the same type of sputtering process that we use for the metal layers, with the exception of a couple of the first layers that we put down. We put down some really thin layers at first just to provide a little protection before we go to the high power, thick, fast depositions. And so the thin layers we put down at first, again, are being put down with an RF sputtering rather than the DC sputtering. So they're put down with 13.5 megahertz, and they grow slowly but provide protection for the process. Once the ITO is down, then the material again goes back and visits the lasers, and it actually gets the ITO scribed on top with the laser. It's a really shallow scribe because you only want to go through the ITO into that insulating layer that we had put down initially, and it just basically cuts the cells apart on top. So the first scribe we do, the through scribe, cuts through the whole silicon stack in the metal. The second scribe we do connects the silver down to the aluminum. So the silver from this cell here to the aluminum on the next cell, so top to bottom, to get them series strung. And then the last scribe is the top contact cut, which basically cuts the ITO between each cell so that you aren't shorted on top. And so then the current's going to travel from the positive down through and then to the next cell, down through, and kind of weaves its way through the things. So you've got the whole module series connected. So each one of your modules, if you look at a 60 watt or 120 watt, if you count across, there's going to be 13 cells. Each of those cells are connected in series with that laser scribing process and screen printing process to make the one individual 15 volt module.